Welcome to this video on phosphorus recycling for organic agriculture, which was made in the frame of the Core Organic project Improve P, which was granted by the core organic funding bodies of Austria, Denmark, Germany, Great Britain, Norway and Switzerland. The project was coordinated by Kurt Möller from the University of Hohenheim, Germany. The main objectives of the Improve P project were to evaluate different approaches for an efficient phosphorus recycling. Firstly, to assess available wastes and recycling technologies. Then, to study the phosphorus forms and the phosphorus availability in the different products. To assess the risk of accumulation of potentially toxic elements. To look at the environmental impact, doing a life cycle assessment. To look at aspects of regulation. And finally, to assess the acceptance of the different products among stakeholders. So we will look at these different aspects in this order in this video. And in the end, we try to draw some conclusions on the pros and cons of the different recycled P fertilizers. Why is it so important to study phosphorus? First of all, it is an essential nutrient for all organisms. It's important for the energy metabolism of each cell, it's in our genetic material, and it's also in teeth and bones. Secondly, it's a non-renewable resource. There are very few mineable phosphate deposits around the world, and they are unevenly distributed on the planet. So there are huge deposits in Morocco, for example, but very few mineable deposits in Europe. Last but not least, phosphorus is also an important environmental pollutant, which can decrease biodiversity in natural ecosystems and can cause dangerous algal blooms in water bodies. The internal phosphorus cycle between plant and animal production on a farm is very important. Phosphorus contained in feedstuff is partly excreted again in the form of animal manure and can be brought back to the soil. But as soon as plant or animal products are exported from the farm, we have also an export of phosphorus in these products. Therefore, we need external inputs to the farm. These can be in the form of purchased feedstuff or fertilizers. The typical phosphorus export with harvested products is in the order of 30 kg phosphorus per hectare, mainly in grains. In a typical arable soil in Europe, we would find approximately 2,000 kg of phosphorus per hectare in the top 20 centimeters, half of which would be in inorganic and the other half in organic form. Now, if we look at the effect of phosphorus export from the system, we can see that without any substitution of the exported phosphorus, we would deplete the soil phosphorus reserves by about 50% in 50 years. And even if there is some substitution, we can still see a significant depletion over, for example, 50 years. A recent study in Germany found that on ecologically farmed areas, only about 35% of the area is in the optimum range of available phosphorus in the soil. About 25% were high to very high in available phosphorus, and this occurs often under vegetable farming with a lot of compost application. But critically, 41% of the area was low to very low in available phosphorus. And this is probably a result of the negative phosphorus balances that often occur on organic farms. There are a few general principles that are important for phosphorus management in organic agriculture. Firstly, organic agriculture aims to nourish plants through the soil, so to foster life in the soil. Therefore, synthetic mineral nitrogen fertilizers or highly soluble phosphorus mineral fertilizers are not allowed. There is also the principle of ecology, which means that nutrient cycles should be closed as much as possible. And there is the principle of care, which aims at protecting the health of both current and future generations, and also to protect the environment. Allowed external phosphorus sources in organic farming are therefore rock phosphate, meat and bone meal, and multi-nutrient fertilizers such as chicken manure pellets. To close nutrient cycles, it would be important to use urban organic wastes, animal wastes, and sewage sludge and urine as much as possible.
The base of any improvement of phosphorus recycling is to have an inventory. What are our potentials in our societies? And the main potential in our society is sewage sludge, with more than 50% of the phosphorus cycling in our societies in the sewage sludge. The second main potential is the municipal solid waste, with all these household organic wastes. And the third most important potential feedstock for phosphorus recycling is meat and bone meal, the residues of our slaughterhouses. For each of these feedstocks we have very different approaches for treatment. Theoretically, at least, each of these feedstock we can apply directly to the field after stabilization and hygienization. And more advanced approaches to recover the phosphorus of sewage sludge is either precipitation, a physico-chemical approach, or a thermal approach in order to get ashes or chars or slags. And for meat and bone meal, we can either apply thermal approaches also to get ashes, biochars or slags, or to use it directly in the field or as animal feed. For urban organic wastes, we can either feed them to animals to prepare a compost or to recover energy in anaerobic fermenter, and as byproduct we will get digestate. We have large differences in the phosphorus recovery rates, with high for direct field application and for incineration approaches, and low to intermediate phosphorus recovery rates for physico and physico-chemical approaches. The most approaches for more advanced recovery are related to losses of organic matter and other nutrients like nitrogen and sulfur.
So we have seen different possibilities to produce recycled phosphorus fertilizers from the three main categories of wastes. And the question is now, how available is the phosphorus in these different recycled phosphorus fertilizers? What are the processes behind? And are there any important interactions with soils and plants?
When using recycled phosphorus fertilizers, the most important trait of these fertilizers for the farmers is that the phosphorus contained in these materials is available to the crops. Several studies have already been carried out to determine the availability of phosphorus contained in these fertilizers to crops. However, when we started Improve P, these studies they were dispersed, and also newer products were around that we then tested in own experiments. When studying phosphorus availability in recycled phosphorus fertilizers, the challenge is that these are complex fertilizers. They do not contain phosphorus just in one form like the commercial water-soluble phosphorus fertilizers, but these are complex fertilizers containing different phases and compounds of phosphorus, and also other elements and materials such as organic matter. The phosphorus availability of recycled phosphorus fertilizers to plants depends on the fertilizer's properties, such as the phosphorus forms and their solubility, but also on the soil properties, the pH and the phosphorus status of the soil, for instance. The plants also affect the availability, for instance, by their phosphorus need, but also by their phosphorus acquisition strategies. Finally, fertilizer application, the soil and crop management, and also the climate will affect the phosphorus use by the crop. When we characterize the phosphorus availability of recycled phosphorus fertilizers, then first we characterize the phosphorus forms and the solubility of the fertilizer, and then we study them in incubation studies using soil fertilizer mixtures, and finally in the presence of plants in pots or field studies. The characterization of the phosphorus fertilizers is currently done using chemical extractions. We know that the water solubility and the citric acid solubility are not good indicators for the phosphorus availability to plants. This is why recently also other chemical approaches have been tested, and it was shown that sequential extraction using anion exchange resins and bicarbonate, for instance, are well related to the phosphorus uptake from the fertilizer by the plants. When coming to the plant tests that we compiled from the literature published on field and pot studies, but also on own pot studies, then we used an indicator on phosphorus availability obtained from the difference method. This method is based on the comparison of the phosphorus uptake by a plant from a non-fertilized treatment, from a water-soluble phosphorus fertilized treatment, and from the treatment with the recycled phosphorus fertilizer. And then the increase in phosphorus uptake from the water-soluble fertilizer compared to the zero phosphorus treatment and the increase in uptake from the recycled phosphorus fertilizer are compared and expressed as an indicator on phosphorus availability, which is called the relative phosphorus effectiveness. For instance, a relative phosphorus effectiveness of 30% means that the recycled phosphorus fertilizer has an availability of 30% compared to the water-soluble reference fertilizer. Here we see a summary of the results that were compiled in the Improve-P project. Rock phosphate, which is admitted in organic farming, has a relative effectiveness of nearly 0 to less than 50%. Then we see that we have recycled phosphorus fertilizers such as True White, which is as available to crops as a water-soluble reference fertilizer. We have a broad band of availabilities of recycled P fertilizers, but most, except maybe the untreated ashes, have a greater relative phosphorus effectiveness than rock P. We also see that the effectiveness of a given fertilizer varies broadly. And one reason behind this is, for instance, the soil pH. Now, coming to the effect that the plant can exert on the availability of the phosphorus from the recycled P fertilizer, I here show results obtained in a pot study with Italian ryegrass, rapeseed and alfalfa. Rapeseed and alfalfa are known for their ability to acidify the rhizosphere. And here we can see that most probably as a result of this acidification, they used the phosphorus applied in form of a chemically treated sewage sludge ash more efficiently than ryegrass could use it. I come to the conclusion there exist good alternatives among the recycled phosphorus fertilizers to rock phosphate. Water solubility is not an important criteria, as for instance seen for the True Whites, The phosphorus contained in struvite is hardly water soluble, but they are as available to crops as a fully water soluble mineral fertilizer. The choice of the recycled phosphorus fertilizers depends on the soil pH. Struvite, for instance, is available to crops across a wide range of soil pH values. On the other hand, phosphorus contained in sewage sludge ashes will be available to crops mostly in acidic or slightly acidic soils. Some crops can mobilize phosphorus from hardly available phosphorus sources. This is something that could be considered, for instance, in crop rotations or in the choice of cover crops. Thus, using an integrated nutrient management approach that considers the properties of the soil, the crop, and the fertilizer will result in an efficient use of phosphorus contained in recycled phosphorus fertilizers in organic farming.
Recycled phosphorus fertilizers do not have only a positive effect on plant growth and plant availability for phosphorus, but they also imply a potential dispersal of a wide range of contaminants like pharmaceuticals, like persistent organic pollutants, plastics, and potentially toxic elements, often referred as heavy metals, to the soil and to the surrounding environment. And the overall risk assessment for cadmium show that for several of the currently allowed recycled fertilizers like compost, phosphate rock, and some digestates, the risk is higher for cadmium accumulation in the soil over 200 years than for several not allowed recycled fertilizers, including seared sludge, including digestates of catering waste, including struvite or some ashes and slags. And this shows that the current approach to assess the suitability of any recycled fertilizers just related to the dry matter content of the fertilizers is not suited for real risk assessment, and we know better approaches to assess the suitability of recycled fertilizers. One ratio is the cadmium to phosphorus ratio in recycled fertilizers. It's a rather simple approach, and you can see that for green waste compost, for example, you will have 6 to 8 times more cadmium per unit phosphorus than for sewered sludge. And you can see that the phosphate rock have even much higher cadmium contents per unit phosphorus. And you can also see that meat and bone meal, as well as struvites, have an extremely low content of cadmium per unit of phosphorus. We can conclude that potentially toxic elements are not further a major concern, but we know at the same time that there are feedstocks with high concentrations of potentially toxic elements, which will mean we need a monitoring to avoid to use highly contaminated feedstocks. And at the same time, we do need new approaches for assessment of the loads of potentially toxic element in recycled fertilizers, taking into consideration not only the concentration of potentially toxic element, but also the concentration of phosphorus or phosphorus in combination with other nutrients like nitrogen or potassium, to get a more balanced value for assessment of the suitability for use in agriculture. In Improve P, we were not able to assess the risk for plastic or for drug substances, and therefore in a literature review we checked the available data, and we found a very comprehensive Norwegian study carried out by the Norwegian Panel of Food Safety, and they assessed the risk of more than 1,400 drug substances, including a lot of pharmaceuticals, and only 14 have been estimated to exceed the cutoff values in the soil. after sludge application, and the overall conclusion of the panel is that treated sewage sludge, or at least Norwegian sewage sludge, represent a low risk for soil ecosystems in terms of drug substances. A very new aspect are plastics, microplastic and nanoplastics. And we know that not only biosolids may contain plastic, but also urban compost and urban digestates. That the degradation of plastic in the soil is a very low process, taking a lot of time, and this degradation is enhanced by solar irradiation as well as by high biological activity.
To evaluate the environmental impact of the different options for recycling, we conducted a life cycle assessment. And this is the work of Steffen Hörtenhuber from Fiebel Austria and others. So we assessed 5 main categories. Firstly, the abiotic resource depletion potential, which refers to the mining of rock phosphate and the use of chemicals during the process. Then the energy demand, which includes fossil fuel demand as well as production of biogas, which would be positive. Then the global warming potential, which refers to all gaseous emissions. And finally, the acidification and eutrophication potential of the environment. So here you see a simplified version of the outcome of the LCA analysis. For urban organic wastes, we see relatively little difference between both options, but digestion is a bit better from an environmental viewpoint than composting. The use of meat and bone meal or its ashes has relatively little impact on the environment. All options to recycle phosphorus from sewage sludge, however, have some negative consequences for the environment. Therefore, direct application of sewage sludge would possibly be the best option, at least based on this life cycle analysis. We also analyzed the different regulations regarding the use of fertilizers in organic agriculture, and this is the work of Anne-Christine Loos et al. 2016. So in the EU regulations, authorized fertilizer inputs should be natural substances of plant, animal, microbial or mineral origin. But these EU regulations are translated differently by national laws, retailer requirements or private standards. When we compared the different national standards, we found that the input of conventional manure is limited in the amounts in most countries except Norway, that catering waste is not accepted in several countries, and that overall 80 to 90% of the potential phosphorus sources for recycling from society are actually banned for organic agriculture. In our opinion, the definition of what a natural substance is needs to be clarified. We have also seen that it is quite challenging for the regulators to keep up with the rapid technological development that is currently occurring. We also conducted some workshops to find out what the organic sector thinks about different phosphorus fertilizers. In total, we conducted 9 workshops with different stakeholders, and during these workshops, we first informed them on the important aspects of recycled phosphorus fertilizers, and afterwards stakeholders were asked to fill out questionnaires. We can see that the majority of participants became more positive towards recycled phosphorus fertilizers as a result of the information that they received. So we can conclude that the lack of acceptance of recycled fertilizers can be a result of lack of information. We saw that the acceptability of urban organic wastes, excluding animal residues, is generally very high. With respect to conventional manure, manure of ruminants is much more acceptable than manure of pigs and poultry. For meat and bone meal, we had also generally quite high acceptance, and definitely much higher than for rock phosphate and basic slag. With respect to human wastes, we saw more than 50% acceptance of urine in all countries. Whereas sewage sludge was generally seen more critically, especially in German-speaking countries. Stakeholders were also asked to say whether they agreed or disagreed with the following statement, that permitting more recycled fertilizers in organic systems would damage the reputation of organic food. The outcome was that about 20% agreed with the statement, but 50% disagreed more or less strongly, and the remainder was indifferent. This suggests that there is scope for more use of recycled fertilizers in organic agriculture. So from the Improve P project we can conclude that many recycled phosphorus fertilizers that are currently not permitted have lower environmental impacts than some inputs that are already permitted, such as compost and phosphate rock. Also, the plant availability of phosphorus in many recycled phosphorus fertilizers is higher than that of phosphate rock. Therefore, if a farmer needs external phosphorus inputs, recycled phosphorus fertilizers should be preferred over phosphate rock. We have also seen that neutral and alkaline soils are the most challenging soils in terms of finding a suitable fertilizer source. We have seen that struvite has a very high efficiency, even in neutral and alkaline soils, but incineration ashes and meat and bone meal are basically inefficient in alkaline soils. With respect to the risk assessment, we have seen that potentially toxic elements are not further the main constraint that limits the recycling of most recycled phosphorus fertilizers. For organic pollutants, there are still some uncertainties about risks to human health and the environment. We have seen that all approaches to reduce the risks from organic pollutants have several shortcomings, such as reduced phosphorus recovery rates, or increased greenhouse gases, or lower P fertilizer values. Therefore, it is very important to reduce the potentially toxic elements and the organic pollutants already at the source. All recycling bears some risk of contamination, but if for this reason recycling is neglected completely, then we will depend on non-renewable abiotic resources. Therefore, it is so important to assess the real risks. In other words, to find a good balance between the principle of ecology and the principle of care. So here we try to compile the conclusions with respect to the different categories in a simplified matrix, showing green for a positive assessment, neutral or acceptable in gray, and negative in red. As you can see, none of the options is the silver bullet for recycling. Each option has advantages and disadvantages. And we think it is important to assess not only the quality of the products, but also to assess the overall environmental impact of the process. So we have seen that with respect to phosphorus recovery, the struvite crystallization has a low performance. The phosphorus fertilizer value is quite bad for meat and bone meal ashes, and all incineration processes naturally destroy organic matter. The accumulation of organic pollutants is still a problem with direct application of sewage sludge, and the environmental impact, so the summary of the LCA analysis, shows a bad result for biowaste compost and struvite produced under the Stuttgart process. This cannot yet be the final conclusion because new solutions are still being developed, for example the alkaline pyrolysis of dried sewage sludge. And to come to an overall ranking, the weighting of the different categories is fundamental. So some final remarks with respect to organic agriculture. The natural processes of composting or digestion have the big advantage of preserving carbon and organic matter for the soil. If sophisticated methods of organic waste treatment are used, they should be combined with some added value, such as energy production or the recovery of nutrients other than phosphorus. And we think it is very important that we get a better differentiation between low risk and high risk material, So for example, sewage sludge from non-industrialized areas versus sewage sludge from large cities. If you would like to find out more about the project and its outcomes, please consult our website, where you also find the link to our publications on organic e-prints.